Okay, this video is going to serve as a preview for week 9, the week after Thanksgiving. I'll get this posted prior to uh, coming back from after Thanksgiving, so you'll be ready for you. We're going to focus on the Atterberg limits in week 9. Read through the chapter a few times back and forth. Found some things there and some other places, so I put together some notes. I'm I haven't quite got them complete, but uh, what's left I feel like can finish up during the video here. I don't get mixed up. So this is all about soil consistency. It's in your book. I believe it's in section 2, 3. I'm not sure what the page is, but you can find it there. And I encourage you to read through it. It's a little bit hard to sort out. I found some more material and I took notes from that also. And hopefully, this will, I want us to leave here with exposure for sure to uh, these ideas, these tests, these indicators and parameters, and some nomenclature. But I also want it to sink in a little bit, and we carry it with us. Uh, so I decided to put up a video, and you can pause it, take notes, or maybe you'll get what you need out of the textbook. But the Atterberg limits were developed by a fellow named Atterberg quite a while ago, experimenting with the effect of water on soil. And he did run several tests and came up with this plasticity chart, which we'll get to later. Uh, but consistency in, as you can see here, consistency in cohesive soils refers to its degree of firmness. It's like Play-Doh down to mud to the consistency of a milkshake, let's say. It's the concern of engineers is how soil behaves under different moisture contents. So Atterberg's tests are relate to moisture content consistently. His They provide an easy way to relate behaviors behaviors as they relate to the moisture content, the addition of and taken away from. I think you'll find this little chart in your in your textbook, but it's just showing you on this horizontal axis is the transition from solid to semi-solid to plastic, and then we throw in a little deal of this difference right here gives you your plasticity index, the pi here, the liquid limit minus the plastic limit. And the plasticity index we've used before in calculating the group. I think it was the group, uh, yeah, the group number. I think it was. Is that what it was? Anyway, it was that big formula we used. So we've used it a couple of times, and it'll be in your ASHTO chart and a given in there that you will be using. So we have the shrink limit, which is a solid. We have the plastic limit, which is a semi-solid, and we have a liquid limit. But the illustration of this chart is as we're adding moisture content, notice that the volume is increasing uh, as you're doing a proctor test, which hopefully we'll have time to before the end of the course. Uh, I spend in week 10, we're going to look at tests uh, to finish off the course. So again, you keep adding water, and your volume keeps it getting larger. Now in a Proctor test, you want to find that zone where that when as you add a water and compact at the same time, the volume stays the same, but the density increases. So the shrink limit is the water content below which the soil volume remains constant. The plastic limit is the water content at which the soil begins to crumble when it's rolled into an eighth of an inch thread on a table. And what you're doing is you're gradually removing the water, and you weigh it before you start rolling it, and then when it starts to crumble, there's a picture of it in your book. That would be your plastic limit. So the liquid limit is what divides the liquid state. The liquid limit is the dividing line between the liquid and the plastic. The liquid and the plastic. That is the liquid limit. So we go solid, semi-solid, plastic, liquid. Okay, let's see what else we have down here. And we have the plasticity index is defined as the plastic limit right here. The liquid limit minus the plastic limit gives you the plasticity index. As we will be getting to the unified, most of our work so far has been centered around the AASHTO because of the calculations and the concreteness of it. The unified soil will be a little bit more complicated because it's kind of like a flow chart, but we'll get it done. But this is part of the unified soil classification system, and it's called the Casagrande. That was this guy's name that came up with this chart. It's called the plasticity chart, and its main reason is right here to separate the clays from the silt. I've kind of got them, the A line comes from the name Atterberg, separates the clays from the silts. The U line is an indication that there's nothing out here that returns to fine soils. If you look way down here in the corner, you will see there may be a bit. These are plasticity indexes right here of cohesionless, which is coarse soil, and some silt down in here. And this says inorganic silts of low plasticity would be located in here. Here's inorganic silts and the compressibility, and organic silts in here, inorganic silts of high compressibility, and then it's the vertical, the 50% liquid limit line. If you go vertically up under a line, separates the high plasticity fines from the low plasticity. It separates the clays, the high plasticity clays, from the low plasticity clays. That's that little line right there. And you know, if you take it up, you would have all of these would be high, these would be low. Let's see, what are these notes? You know, you think we've talked a little bit about a hydrometer test early on, even in the erosion class it was brought up, I think. But a hydrometer test, the question is if we can tell a fine-grained soil, if you can tell it's a clay or a silt from this chart, why in the world do we need to perform a hydrometer test? It's a question I found in my readings. Well, the tests measure different things. The hydrometer test measures the composition of the soil. In other words, it measures the actual particle sizes. The Atterberg limit is a measure of the behavior of the soil in the presence of water. As you can see so far, water's entered into all of these limits, and shrink and swell, we dealt with it early on. So let's see what I want to talk about. Just a couple more things, and I'll probably have to jot them down quickly as I write them. You know, the question I ask is, why are these things important? Why are these Atterberg limits important? And they're used to complete, for one, the liquidity index. And the liquidity index is it's a measure of soil sensitivity. It's a measure of soil sensitivity. Or an indication. It has a formula. The liquidity index is Li for liquidity index equals, let me think, the moisture content, put a little W there, minus the plastic limit divided by the plasticity index. And that gives you well, it's kind of like the sensitivity is is it hard, soft, the shear strength, and things like that. In other words, will it stand up to compression? There's a little chart I found. I think it's in the book too, and just to get an indication, these things would be you would get information from this soil numerically that would indicate its strength also. So I saw this chart, I think I saw it in the book or somewhere, just to talk about results of this on a chart, where this would be stress over here, and this would be what they call axial strain. Yeah, axial strain, T-R-A-I-N, and that's strain in the direction of force, whether it be shear or straight down. That's just all that means. It's actual is like this is an x-axis, this is a y or horizontal axis. So it's the strain in the direction. So I saw in the book that there were attempts to have me understand, but I had to go elsewhere. It showed a curve like this. And he labeled it, or the book labeled it in the little table as maybe, it's called strain hardening. And that would be strong. I'm just going to throw that in there. That would be strong. A good structural base, a good base for our structure. And then it has some soil measurements that plot out like this. And this would be strain softening. In other words, it does okay, and at one point it starts to weaken. So you would be wanting to investigate that soil further. And then they had one that just kind of shot up and just went right back down pretty quick. And that right there is a drastic drop in strength. I don't know. It's a very sensitive soil. Very sensitive. Right down a drastic drop in strength. Okay. So it's what what's the connection here? It's just all processes that are related to the Atterberg limits. All of these things are related, and it goes deeper and deeper into the classification of the soil. Uh, so liquidity indexes, now they're going to be, I meant to say this a while ago, but they're going to be like 1, maybe greater than 3, or between 0 and between 0. Oh, I'm just trying to make up some things. And 3, so 2, something like that. But there'll be results like this: 1, or greater than 3, greater than 1. But I'll try to define that. There's some samples that I found. I'll jot down. Let's see, where's my paper orientation here? So if the liquidity index is greater than 1, let's say, these are kind of rules of thumb. The liquidity index is greater than 1, the soil, I won't say it, the soil see, I lost my place. If it's greater than 1, the soil is probably, let's call it good. It would be up in this area, the stronger soil. If it is a good indicator that this is a good, I'm sorry, I got this wrong. If the liquidity index, I jotted this down, is greater than 1, it's a good, not good soil, it's a good indicator that that you have a sensitive soil. Should have had all these written down, but that's okay. So you would need to investigate that soil a little bit. You better look into it a little more. Now, what I started to say, liquidity index, well, below 1, the soil is most likely not sensitive. It wouldn't require further investigation, most likely. So there's one of the reasons why we can calculate the liquidity index. And the where did I see that? I haven't gotten to it yet. Let's see, what else do I have written down here that I want to share? There's a pencil. So it's a that's one. Here's another. It's an indicator of the clay type. Indicator of the clay type. By the way, it uses Atterberg Limits. It uses a hydrometer. Uses a hydrometer with the Atterberg Limits. It uses a hydrometer to test and to compute the activity of clay. To test and compute the activity. I'm going to capitalize that because that's a thing. Activity of clay. All right. Now, that's called activity level. That's kind of important. Activity level of clay. What's going on inside the sample? And the hydrometer lets us, oh, here's the calculation for that. A, activity, and then we'll move on. Activity equals A equals the plasticity index divided by the percent of clay fraction. And that is given I think it'll come to me as I'm going through this, but it's a given. Oh, it comes from the hydrometer test. That's where it comes. The clay fraction result hydrometer test. Sorry about that. Okay, so we got this and we got that. It computes the liquidity index and it tells us something about clay, and I'm going to show you that on my next page. The story it talks about clay, and there's a video coming at you at some point about how clay is comprised, the composition, the plates, and the different kinds of clay. All of those are real important, and we probably, where's that line? Oh. And I'm not sure how far we will get into it, but what the clay is made from, like silicon or other things, makes a difference about the water and the role it plays. So we have the computation of the activity, and that's the plasticity index divided by the percent clay fraction, which is obtained from the hydrometer test. Now, what else? Oh, the clay needs some more clay info. Down here, more clay in formation. There's a chart that I saw, or another somewhere. So, for instance, now this is in the presence of activity in the presence of water. Okay, so the activity level of clay, let me just kind of overlap. Level, which is computed by, I'm going to repeat that, is the plasticity index divided by the percent clay fraction. And you will get results of like we did with the strength or the stress strain, you know, of like 1 and less than or more than. But I do have an example here of, and this is in the how active clay is in presence of water. So if you have, if we come up with like activity level if we come up with an activity level of 1 or greater, then it's a pretty active soil sample, and you may have problems. with swell. Or, speaking, or chemically. Why did I say chemically? Chemically. All of these clays have chemical compositions, electro, whatever goings on, and they also contain ions. Now that's a chemical term, and they're called cations. And ions are in chemistry and atoms and have to do with the uh, element classifications and things like that. But so you may have problems with swell and ions. You may be adding ions, adding ions when you shouldn't be in like stabilizing the soil. So if it's greater than one, it's pretty active and you may have problems with swell and or certain ions. This little chart, I want to show it. It's not going to tell us a whole lot, but I'm beginning to be a plotting dude here. Plasticity index going in this direction, and the percent clay. And of course, you would be plotting a graph here like this, and you may have one that plots up like this, and that one may have a activity level of 1 to 5. If it's got that, the chart I looked at would tell me that that was Montmorillonite. Montmorillonite. Get used to these if you stay in soils, Montmorillonite. And then you may have a plot coming out this way, which may have illite, which is Illite, and it may be equal 0.5 to 1.0. And then there are things like the kaolinite, which may equal, and these are not accurate, they're just typical of these types of clay. And clay comes in shelves and plateaus. We'll get around to that, but this stuff, uh, I'm not expecting you to memorize all of this stuff. I just want you to know about these things for sure. So this would be 0.4. So this right here, probably wouldn't be affected by water. Effect of H2O be minimal. When they start to get up in this area, H2O, effectiveness goes up. But rule of thumb time. If the activity level if the activity level is low, which is 0.4 to 0.5, the soil is relatively inert, and let's just call that quiet. Quiet. It's not much activity. So, and will not react adversely to water. Water. Okay. A couple of things left. This is like 1, 2, 3. This is like 4 that we've gone through, and I need one more sheet of paper to finish this off. Finish us off. More of the significance of limits. More of the significance of Atterberg limits. Well, I can't seem to get lined up here. So let me start right about here. It's also an indicator of swelling potential. And in what way? If the soil has a PI, a plasticity index, if soil has a PI that is, is greater than 20, plasticity index greater than 20, then you probably have a soil prone to shrinking soil. Then you probably have a soil prone to shrink and swell. It's also an indication. It's also an indication They are also an indication of stress history. We talked a little bit about stress and strain earlier. So here's one. Rules of thumb, I call them, but rules. If the liquidity indicator index, if the liquidity index is greater than or equal to 1, the soil is most likely normally consolidated. Now, it's experiencing currently its maximum load. So if we're looking at a site and we get a liquidity index and it happens to be greater than or equal to 1, it's normally consolidated. It normally is experiencing now its maximum load. Now, do we want to add to that? Because you can also say, or the greatest stress ever. Greatest stress ever. So we don't want to add to it. Another, it means that the soil is pretty strong, but may not be prone to settlement or deformation and have a high shear strength. Maybe. Oh, that's the next one. I'm sorry, I'm ahead of myself. So this one, we'll be cautious. Now, if it has, if the liquidity index is less than 1, it's a fraction, then the soil is probably over consolidated. The soil probably over consolidated. So what does that mean? The soil has experienced its greatest load in the past, which means that the soil is pretty strong and it may not be prone to settlement and deformation. Has experienced its greatest load already in the past. And what that means is it's probably the soil is probably strong and has a and won't be prone to settlements and deformation. And probably won't be prone to settlement and deformation. And as I think of it, it should have a high shear strength. Okay, one more. Why we like Atterberg limits. It's used to classify. It's used to classify soil types, as we're doing now under the unified soil classification. I said we're doing now, but we hadn't quite gotten to the unified classification system, but we will. And that part is, this is used under the unified soil system to separate clays, silts, and then there's another parameter to coarse grain and fine sands, etc. So that's it. That's a lot. Took a while, but I think in addition to reading your chapter, this will give you some more information, hopefully useful, and there. So probably be checking in with you maybe during Thanksgiving, after. If you have any questions, I'll be available. Be out of town for a spell visiting a daughter down in Beaumont and her boy. And but pick up that phone now if you need anything. Have a happy Thanksgiving.